Hello, Matthews Gatos here. In this video, we're going to talk about natural logs, what they are, how to graph them, how to figure out limits, and how to simplify expressions involving them. So what a natural log is it's just a special case of a log. So common base logs, if I just say like y equals log x, it has a base of 10. If I were to take a log and use a base of e, now what's e? E is an irrational number, kind of like pi. You know how pi is an irrational number, and we all know pi to be about 3.14? E is also another irrational number, and it has a value of about 2.7. So if I were to take a log with a base of e, which is about 2.7, first thing I know is it's an increasing log graph. Second thing, because it's such a special base, it has a special name. So the log base e of x is actually called ln x, which is natural log. So it's a log with a base of e, but it has its own name, which is ln x. Okay, so it's an increasing log function because we know the value of e is about 2.7. So that's what a natural log is. Let's look at the graphs. So just like we did in the graphs in the last one, we looked at y equals b to the x, and then we looked at log base b of x. We're going to do the same thing, except the base now is going to be e. So the base is e, which is just that special irrational number that has a value of about 2.7. So looking at the graph, this is the graph of y equals e to the x. So it's an exponential graph that's increasing. So it has all those properties that exponential graphs have. No x-intercept, a y-intercept of 1, a vertical asymptote, there is none, and a horizontal asymptote of y equal to 0. The domain has no limits, the range just has to be greater than 0. So the inverse of e to the x is ln x, which is log base e of x. And it has the same properties of an increasing log graph. So x-intercept of 1, no x, no y-intercept, no horizontal asymptote, but it has a vertical asymptote at 0, and the domain and the range are interchanged. So what we're going to do is use our understanding of logs to be able to find out limits using e to the x and ln x. So let's look at our first case, which is the exponential graph, e to the x. So I have a little sketch of it below. So e to the x, where the base is e, just means it's an increasing exponential function. So if I want to look at the limit as x approaches positive infinity, so I want to take it where x is getting infinitely big. So x is getting bigger and bigger and bigger. You can see the value of my function is going towards positive infinity. Let's look at the case where I'm approaching 0 from the right. So from the right of 0. So as I'm getting closer and closer and closer and closer to 0, you can see that my function is going to a value of 1. And actually, in this one here, I could just sub my limiting value in. And e to the x, well, any base to the exponent of 0 is just equal to 1. So I see it graphically and also by substituting it in. Now let's look at the natural log graph. So the natural log graph is just a log graph that is increasing because it has a base that is increasing. Okay, so looking at this graph here, there we go. So I want to look at the limit as x approaches positive infinity of ln x. So as I make x infinitely big, so as x gets bigger and bigger and bigger, this graph is going to grow without bound, and it's going to approach towards positive infinity. Let's look at the limit as it approaches 0 from the right. So it can only approach 0 from the right because there's a vertical asymptote there, so it can't approach it from the left. So I get closer and closer and closer to 0 from the right. You can see that this graph goes down towards negative infinity. So this is going to be another case of looking at the graphs is going to really help us, so knowing our graphs. So let's evaluate some limits. If I look at the limit as x approaches negative infinity of e to the negative x, well, you can see here I have the graph of e to the x, but I have a negative x, which just means I've done a horizontal reflection. So I'm going to take this graph here and I'm going to do a horizontal reflection. So it's going to still have my y-intercept at 1, but instead of being an increasing graph, I'm going to reflect it about the y-axis, and it will be a decreasing graph like that. So now that I know what my graph looks like, I can look at the limit as x approaches negative infinity. So as x gets smaller and smaller in the negative direction. So as I go here and I get smaller and smaller and smaller for x, you can see that my function is growing without bound, and it will actually be positive infinity. Okay, my next question here. The limit as x approaches 0 of e to the x squared plus 1. So my little tip here, if you can sub in the limiting value, you sub it in. We can't substitute in infinity, but we can, in this case, substitute in 0. So the limit as x approaches 0 of e to the x squared plus 1 will be equal to e to the 0 squared plus 1, which is just e to the 1. So this limit will approach a value of just e. Okay, in this next one, the limit as x approaches positive infinity of e to the negative x squared. So I can't substitute in positive infinity. I also can't draw that graph. I don't know exactly what that graph would look like because it's not e to the negative x, it's e to the negative x squared. So if you can't draw a graph or sub it in, try subbing a number in, or just the idea of what the numbers would be. So for example, positive infinity. Positive infinity is a really big number. So if we were to sub this in, we'd have e to the negative big number squared. So a big number squared is an even bigger number. So when we have a big number squared, I'm going to really write that in all capitals as a really big number. So e to the negative big number, well, that's really the same as e to the negative 1 to a really big number. So that's 1 over e to a really big number, which is just really 1 over e to a big number. So e is already a number greater than 1, and I'm raising it to a really big exponent. So as this big number on the denominator gets bigger and bigger and bigger, this whole thing will approach to 0. So as the denominator gets bigger and bigger and bigger, 1 over a really big number is going to approach 0. So I know that that is 0. So my first choice is always looking at the graph or subbing the limiting value in. If I don't, then I just kind of think about it logically and work through like that. Okay, in this next example, I have the limit as x approaches positive infinity of ln 1 over x. So this is the graph of ln x. So I'm just going to manipulate this formula a little bit here. So x approaching positive infinity, I'm going to write that as ln of x to the negative 1. 1 over x is the same as x to the negative 1. And bringing that negative down, that's the same as the limit as x approaches positive infinity of negative ln x. So that's just going to be a reflection. Okay, it's going to be a reflection vertically. So this graph here, that's an increasing graph with an x-intercept of 1, when I reflect it vertically, will be a decreasing graph with an x-intercept of 1. So something like that. So if I look at the limit as x approaches positive infinity, that means that x is going to be getting bigger and bigger. I want to know what's happening to y. So as x gets bigger and bigger and bigger, you can see that y is going towards negative infinity. So this limit would be negative infinity. Okay, in this one here, the limit as x approaches negative infinity of the natural log of absolute value x. So absolute value of x means whatever is inputted, positive or negative, the output will be positive. But if you look at ln x, all of the x's already are positive. So the graph won't look any different than that, because the limit as x approaches negative infinity of natural log of x is just going to still be the same thing. So what this really is it's going to be the limit as x approaches negative infinity of a really big positive number. So if I look at this one here, the natural log of a really big positive number, you can see is going to be a really big positive number. So looking at this graph, as x gets bigger and bigger and bigger, x can't be negative. It's going to be bigger and bigger, so this will approach positive infinity. Okay, looking at the next one, the limit as x approaches -5 from the right. So here's the graph of L on x. If I have x plus 5, this plus 5 is on the inside, which is a horizontal translation. Remember, horizontal lies of 5 units left. So I'm going to pick up this whole graph and move it 5 units to the left. So the vertical asymptote at 0 is going to become a vertical asymptote at x equal to -5. The x-intercept at 1 will be an x-intercept at -4. It'll still be an increasing graph. So very rough sketch, just like that. So if I want to look at the limit as it approaches -5 from the left, from the right, I can't approach it from the left, so I'm going to take this and approach it from the right. So I'm going to get closer and closer and closer to -5, and you can see that this graph goes down towards -infinity. Okay, so now that we've done some limits, let's look at some properties of natural logs. They follow the same log laws, like same thing for power law, multiplying, dividing. This one here I really want to draw your attention to. Ln of e equals 1. Here's why. Natural log of e is really log base e of e equals 1. So it's kind of that special case of the matching law. So just remember that the natural log of e is equal to 1. That one comes up a lot. Natural log of 1, just like log of 1, is equal to 0. The natural log of e to the x is equal to x because they cancel each other out. Taking the natural log and taking an exponent with a base of e are inverses of one another, and they undo each other, so it's just x. Same thing here. E as a base raised to a natural log x exponent. Those are inverses and undo each other, and you're just equal to x. So let's do some questions where we're evaluating, expanding, and simplifying some natural logs. So let's try this one here. So the natural log of e to the 4. Well, we can bring that 4 down. So it's 4 times the natural log of e, which we just said was 1. So that's really just 4 times 1, so the answer would be 4. Okay, natural log of 1 over e, 1 over the square root of e, actually. Just going to write that as e to the -1/2. Negative because it was in the denominator, half because it's square root. Let's bring the -1/2 down. So it's 1/2 times the natural log of e, which we just said was 1, and -1/2 times 1 is -1/2. Okay, e to the natural log of 25 exponent. So e and natural log, exponent and natural log cancel each other out. They are inverses of one another, and that just has a value of 25. Okay, let's try some expanding questions. I'm going to use the same rules that I used with logs. The only difference is ln is log base e. So anything that is in the numerator we'll keep there, and we're going to subtract natural log of what's in the denominator. Okay, now fully expanded, we can't have exponents. So this is really natural log. Instead of square root of x squared plus 1, I'm going to write this as x squared plus 1 to the 1/2, because then you can see that the half comes down. So I can write this as 1/2 natural log of x squared plus 1, take away, same thing, the 2 comes down, 2 times the natural log of x. And that's as far as we can go, because there is no law to expand arguments that are added, only arguments that are multiplied or divided. So that would be my final answer. Okay, this one here, we're going to expand this, first of all, as a quotient. So this is the natural log of x squared plus 2 squared, subtract the natural log of ex exponent 4. Subtracting because it's quotient. Okay, anything that has an exponent I of course can bring down. So this is 2 times natural log of x squared plus 2 minus. Now I can't bring this exponent 4 down because the 4 is only for the x, not also for the e. So what I need to do is simplify this. When I have arguments that are multiplied, I can simplify them into logs that are added. So this will be ln e plus ln x exponent 4. Being careful to put it in brackets because we're subtracting the entire sum. So now you can see this 4 can be brought down because it's just by itself with the x. So I have 2 ln x squared plus 2 minus ln e minus, because I have to subtract both of them, 4 ln x. And then just one little thing here, natural log of e is just 1. So I'll write this as 2 ln x squared plus 2 minus 1 minus 4 ln x. And that would be fully expanded. Okay, let's look at number 3. So in this one, because the entire argument is in brackets, I can in fact bring the 5 down. So this will be 5 ln e, the root of x squared plus 1. Now again, I have a product, which I can simplify as adding. So I have 5 ln e plus 5 ln the square root of x squared plus 1. Notice the 5 went to both. Okay, so I know ln e is just 1, so this is really 5 times 1 plus this square root of x squared plus 1. I can rewrite that as x squared plus 1 to the 1/2, because then I can bring the half down. So half down multiplied by the 5 in front is really 5/2 ln x squared plus 1. So final answer, 5 times 1 is 5 plus 5/2 ln x squared plus 1. And that would be fully expanded. So let's try some solving questions, and we'll end with one graphing question. So solving these ones. Okay, so if I have ln x equals to 8, I'm just going to write that in log form, as I know. Log base e of x equals 8. The reason I'm doing that is because log form isn't working for me right now. So I'm going to write it like this because then I can switch it using the circle of logs into exponential form, which will be e to the 8 equals x. And that's just a number. E is an irrational number raised to the exponent of 8, so it's just a number. So I can leave it like that. Okay, in my next example, I want to solve for x, and x is in the exponent. So remember, if exponential form isn't working for you, switch to log form. And I'm going to do that using Bay. Okay, so switching to Bay, I'm going to have log Bay, because we love logs. B stands for base, the base is E. A stands for answer, which is 4. Equals to, E stands for equals to exponent. Now we're trying to solve for x. So log base e of 4 is just ln 4 equals 3 minus 2x. So if I want to get x by itself, I'm going to subtract 3 from both sides. So ln 4 minus 3 equals negative 2x. And then I'm going to divide both sides by negative 2. So ln 4 minus 3 all over negative 2 equals x. Now I could leave it that way, but we really don't like to see negatives in the denominator. So what I'm going to do is multiply top and bottom, to be fair, by negative 1. So a better answer would be negative 1 times ln 4 minus 3. I'm just going to switch those around. 3 minus ln 4 all over positive 2. That would be a better answer. Okay, and in my last question here, I just want to sketch the graphs. Sketch the graphs of y equals negative ln x and y equals ln negative x. So just on the side here, remember that our graph of ln x looks like this. It's an increasing graph because the base is e, which is greater than 1, with a y-intercept of 1. So this is my base graph, ln x. So when I look at ln x multiplied by -1, that is a vertical reflection. So instead of being an increasing graph, it's going to be a decreasing graph because it will be reflected in the x-axis. So I still have my vertical asymptote at x equal to 0. I still have an x-intercept of 1, but if I'm vertically reflecting it, it just means that I'm going to go something like this, where it's decreasing. So I am not looking for perfection. I'm just looking for a sketch. You can label the asymptote, you can label the x-intercept, and of course label the graph. So this would be negative ln x. Now the other graph that I want to do is ln of negative x. And all that is a horizontal reflection. So this one was a vertical reflection. This on the inside is a horizontal reflection. So this graph is going to be reflected over here, about the y-axis. So the asymptote doesn't change, but the x-intercept does. It goes from 1 to -1. Now, if you look at this graph here, it's like I'm taking this graph right here and I'm just literally flipping it to the left. So it's going to look something, and again, it's just a rough sketch, something like that. But you can see that this graph and this graph are mirror images of one another. Okay, and then I will label this one as y equals to ln of negative x. So just a rough sketch of those two. So I hope that introduction of natural logs helped you out and made sense. And I just want to end by asking you this question. What do organic mathematicians throw into their fireplace? Well, hopefully after this lesson you know the answer would be natural logs. Natural because they're organic, of course. So I hope this video helped, and I look forward to seeing you guys for the next one.